A slightly more complicated example is going to be, let's see, y prime equals 1 plus x minus y. It's not a lot more complicated, and as a computer exercise, you'll work with still more complicated ones. But here, the isoclines would be what? Well, I set that equal to c. Can you do the algebra in your head? An isocline will have the equation, this equals c, so I'm going to put the y on the right-hand side and that c on the left-hand side. So it will have the equation y equals 1 plus x minus c. Or a nicer way to write it would be x plus 1 minus c. I guess it really doesn't matter. So there's the equation of the isocline. Let's quickly draw the direction field and see what. Notice, by the way, it's a simple equation, but you cannot separate variables. So I will not, today at any rate, be able to check the answer. I will not be able to get an analytic answer. All we'll be able to do now is get a geometric answer. But notice how quickly, relatively quickly, one can get it. Some feeling for how the solutions behave to this equation. All right. Let's see. What should we plot first? I like c equals 1. No, don't do c equals 1. Let's do c equals 0 first. C equals 0. That's the line. Y equals x plus 1. Okay, let me run and get that chalk. So all isoclines are in orange. If so, when c equals 0, y equals x plus 1, so let's say it's this curve. C equals 0. How about c equals negative 1? Then it's y equals x plus 2. It's this curve. Now let's label it. Let's label it down here. So this is c equals negative 1. C equals negative 2 would be y equals x. No, what am I doing? C equals negative 1 is y equals x plus 2. That's right. Well, how about the other side? If c equals plus 1, well, then it's going to go through the origin. Looks like a little more room down here. How about that one must, so if this is going to be c equals 1, then I sort of get the idea. C equals 2 will look like this. They're all going to be parallel lines because all that's changing is the y-intercept as I do this thing. So here it's c equals 2. C equals, that's probably enough. All right, let's put in the line elements. All right, c equals negative 1. These will be perpendicular. C equals 0, like this. C equals 1. Oh, this is interesting. I can't even draw in the line elements because they seem to coincide with the curve itself, with the line itself. They lie along the line, and that makes it hard to draw them in. How about c equals 2? Well, here the line elements will be slanty. They'll have slope 2. So pretty slanty up. And I can see for c equals 3 in the same way. They're going to be even more slantier up. And here they're going to be even more slanty down. This is not very scientific terminology or mathematical, but you get the idea. Okay, so there's our quick version of the direction field. All we have to do is put in some integral curves now. Well, looks like it's doing this. It gets less slanty. Here it levels out, has slope 0. And now in this part of the plane, the slope seems to be rising, so it must do something like that. This guy must do something like this. I'm a little doubtful of what I should be doing here. How about going from the other side? Well, it rises, gets a little, should it cross this? What should I do? Well, there's one integral curve which is easy to see, It's this one. This line is both an isocline and an integral curve. It's everything, except drawable. So, okay, you understand this is the same line. It's both orange and pink at the same time, but I don't know what combination color that would make. It doesn't look like a line, but you know, be sympathetic. Now the question is, what's happening in this corridor? In the corridor, that's not a mathematical word either, between the isoclines for, well, what are they? They're the isocline for C equals 2 and C equals 0. How does that corridor look? Well, it's something like this. Over here, the lines are all look like that, and here they all look like this. The slope is 1, slope is 2. And a hapless solution gets in there. What's it to do? Well, do you see that if a solution gets in that corridor, an integral curve gets in that corridor, no escape is possible. It's like a lobster trap. You know, the lobster can walk in, but it cannot walk out because the things are always going in. How could it escape? Well, it would have to double back somehow, and remember, to escape, it has to be, to escape on the left side, it must be going horizontally. But how could it do that without doubling back first and having the wrong slope? The slope of everything in this corridor is positive, and to double back and escape, it would at some point have to have negative slope. It can't do that. Well, could it escape on the right-hand side? No, because at the moment when it wants to cross, it will have to have a slope less than this line, but all these spiky guys are pointing it can't escape that way either. So no escape is possible. It has to continue on there. But more than that is true. So solution can't escape. Once it's in there, it can't escape.